All right, let's start with one of the most basic questions you can ask. Why does anything have mass? I mean, the stuff that makes up you, me, the entire universe, it all has weight. But what's really wild is that the most fundamental laws of physics don't automatically require that to be true. So today, we're diving into a huge mystery called the Yang-Mills mass gap, and it's a key piece of the puzzle to understanding why the universe has, well, substance.
Okay, so to get into this, we have to start with a puzzle. And this puzzle involves the most powerful force in all of nature, the strong nuclear force. This is literally the glue that holds the universe together at the most fundamental level.
So here's the thing. The strong force is what binds quarks together inside of protons and neutrons. We know it as carrier particles, they're called gluons, just like light is carried by photons. But here's the huge difference. We have never ever seen a gluon all by itself. They seem to be permanently locked away. So why?
Well, physicists have a name for this problem, and it's pretty straightforward: confinement. It's this idea that quarks and gluons are just permanently trapped inside larger particles. You simply cannot pull one out and study it on its own. And this isn't just a casual observation, it's a really deep feature of how our universe is put together.
To really get our heads around this, we're going to use a fantastic analogy. It takes this incredibly abstract idea from quantum field theory and turns it into something you can almost feel.
Just imagine pouring water. The tiniest bit of energy, right? The slightest nudge, and it flows. Ripples can have any amount of energy, no matter how small. Now think about some thick, cold molasses. You can nudge it gently, and nothing happens. It just sits there. It refuses to move until you apply a certain minimum amount of force. There's a threshold you have to cross.
And that right there is a brilliant way to think about the difference between particles of light and particles of the strong force. Photons are like water. They can have any amount of energy, no matter how tiny. Just think of a long, low-energy radio wave. But gluons are like molasses. There seems to be a minimum energy cost you would have to pay just to get one to even exist at all.
So this minimum energy cost isn't just some quirky feature. It has a formal name, and it is the absolute key to understanding confinement and why so many particles have mass.
It's called the mass gap. In quantum physics, the vacuum is the state of the lowest possible energy. You can think of it as absolute zero. The mass gap means there is a literal gap, a jump in energy, that you have to make to create even the lowest energy particle. You can't just create a tiny little ripple. You have to leap over this gap.
And this visualizes the whole concept perfectly. See, on the bottom, you got the vacuum with zero energy. Then there's just empty space. That's the gap itself. The very first rung on the energy ladder, the first possible particle, exists at a distinct positive energy level. There are simply no states in between.
And this isn't just a theory. The mass gap is absolutely real. We see it. The lightest particle that the strong force can create is called a pion, and it has a mass that's equivalent to about 140 mega-electron volts. That number is a real-world measurement of this minimum energy cost.
Okay, so if the mass gap explains confinement, the next logical question has to be, what explains the mass gap? Why does this gap even exist? Well, the answer is surprisingly elegant, and it comes from pure mathematics. The reason isn't some messy, complicated physical process. It's not some kind of dynamical accident. It is forced into existence by the fundamental geometry of the theory itself.
Let's use one more analogy here. Think of an infinite straight line. You can move any distance along it no matter how infinitesimally small. Its spectrum of positions is continuous. Now think of a circle. If you move around it, you eventually come back to where you started. The positions are kind of discrete. You have these distinct laps. A system that's defined on a circle naturally has a discrete energy spectrum, which means there are gaps between the energy levels.
So here's the crucial point. The mathematical rules that govern the strong force, what physicists call its gauge group, have a specific geometric shape. That shape is compact, which basically just means it's finite and it's closed in on itself just like a circle or a sphere. And because of that circular, closed-off geometry, the possible energy levels are forced to be discrete, like steps on a ladder, not a continuous ramp. And if you have discrete steps, there must be a gap between the bottom, the vacuum, and the very first step.
Just let that sink in for a minute. The mass gap exists because the mathematical space that describes the strong force is finite and closed. The physics is a direct consequence of the underlying geometry. It simply has to be there.
Now this one feature, this gap that's forced by geometry, it has profound consequences. It's not just some abstract mathematical curiosity.
it fundamentally shapes the world we all live in. First, it explains confinement. You can't pull a gluon out because the energy cost to do so never drops below that minimum threshold, that mass gap. Second, it's the origin of the mass for particles like protons and neutrons. Most of their mass doesn't come from the quarks inside them, but from the powerful binding energy of the strong force, which is governed by this gap. And finally, it's why our world has substance. Without the mass gap, the universe might just be a dilute soup of massless, free-flowing energy, kind of like light.
Ultimately, it all comes down to this single, powerful idea. The abstract geometric properties of the mathematical theory are not just a description of the physics, they are the source of the physics. The rules of the game are written in the language of geometry.
And that leaves us with a fascinating final thought. If something as fundamental as mass and substance is a direct consequence of a geometric property, it really makes you wonder, what other profound secrets of our universe aren't waiting to be discovered in a particle accelerator, but are hidden in plain sight, just waiting for us, inside the elegant structures of pure mathematics?